Once a convolutional neural network is fully trained, then the next obvious step is to try and see what is happening inside the intermediate layers of such a network. And there are many ways to actually visualize and analyze these layers, and that's what we are going to talk in the next few lectures. So, one way to do that is uh, choose a layer that you want to kind of visualize and then directly display the weights of those layers as images. So that's what exactly shown in the figures here. So we have four different neural networks which are trained on the ImageNet data set, and we have chosen the very first convolutional layer and extracted the weights of those layers and then directly display them as images. And if we do that, it looks like something like this as shown in this slide. So for example, AlexNet, the first layer has 64 filters and the size is 11 cross 11 cross 3. And if we display them, it looks like oriented edges and opposing colors as we have seen earlier also. And the same is the case with other neural networks as well. Obviously, the VGG19, which has a lower resolution like 3 cross 3, will be having slightly difficult interpretation because of the reduced kernel size. Because if we visualize 3 cross 3 kernel as an image, it looks like 3 cross 3 pixels, right? So we don't get much information out of it. Same is the case with MobileNet, where the kernel size is 3 cross 3, whereas ResNet has a slightly better 7 cross 7 kernel size, and we are able to see the similar trend as in the case of an AlexNet. And the other option is, instead of visualizing the weights as images, why don't we see the outputs of that uh, convolutional layers? So basically, the activations at the output of the convolutional layers. So that is nothing but the weights that we visualized in the earlier slide. When we use that as the kernel and then we pass the images through the network, and what is coming at the output of those kernels after the convolution operation. So that's exactly what we are seeing over here. So the first convolutional layer is again chosen, and the first 7 filters out of, let's say, the 64 filters. So if you choose those, what is the output of those filters when we pass an image? So for example, in this case, an image of a dog is passed through, and what we are seeing over here is basically the texture and the edges of the image are getting extracted at the different filter outputs as, or different kernel outputs, as we can see here. So the different networks are also the same as in the previous slide, and the output is more or less similar, and that's actually quite expected, because what we saw in the previous slide, the kernels or the filters look like edge extractors or color extractors, and that's what we're seeing over here. And obviously, one important thing I would like to point here is these are the outputs of the convolutional layers, and they do have negative and positive values. But once you apply an activation function like ReLU, the output will be more or less above zero and looks much cleaner than this. So what we are going to do is we will quickly go to Colab and try to extract a particular layer, for example, the first convolutional layer, then visualize the weights directly, that is basically imaging of the kernels directly, and then we will see the output of those convolutional layers. And for that, we are going to use a technique known as forward hooking in PyTorch, and I'm going to explain to you that in a moment. So as usual, we are using the ResNet 50 model from the Torch Vision, and then loaded that with the pre-trained ImageNet weights. And we are going to use images from the ImageNet test dataset as well. And if you print the model, it is obviously um, having a lot of layers with the residual connection. What we are going to do now is visualize this first convolutional layer, which is actually con1. Okay, so if we do that, if I scroll down, and of course this is the image that we are going to feed in later, but just wanted to show you here, it's a platypus image, and this is what uh, this is all about. So if we want to load a particular layer from the model, we just need to identify the layer. So it's the convolution one from the model, and the corresponding weights are stored in this particular variable. And then once we have it, we can directly display this as images as shown in this code. And there are 64 of them, and we're going to display all the 64 of them. And then it looks like this, which is very similar to what we saw in the slide, and it is nothing but kind of representing the oriented directions and different colors, and they form the kernels. And of course the size of the kernel is 7 cross 7 in this case. And then the next obvious step that we can actually do is kind of extract the outputs of these layers, right? So for that, what we are going to do is employ the hooking concept in PyTorch, which is shown in these 2 lines of code. So we can actually define a function which kind of store the output value. So for example, a forward hook and backward hook, in fact both of them takes the module and the input output as the uh, in as the variables, and then the output is basically kind of saved for our further usage, because if I want to get the output of an activation layer, I need to store that. We can also do the same for getting the gradients at any layer of the neural network, and for that the concept is same, except that I'm only interested in the first dimension of the gradient output. Okay, so once these classes are defined, the next is obviously to choose the layer of interest, and here I'm going to start with probably the convolutional layer. Okay, so we will choose this layer. So this layer is the last layer uh, in the ResNet 50. So the last convolutional layer in the ResNet 50, and we are going to, so basically this is the full set, and this layer is what we are going to use. This convolutional 3 layer is what we are going to use now. Okay, so let me do that. And then the next is basically the layer is chosen. Now we need to hook the output of that layer, right? So the function forward hook is already defined, so I am initializing that, and then we will define a handler, and that handler will register this function to the respective layer that we are interested in. So target layer we already declared, and we are going to register a forward hook to that target layer. So basically we are kind of trying to get the output of this particular convolutional layer through this forward hooking registration. So once the hook is registered, then of course we need to pass the images through. So that's what we are doing in this step, where we are evaluating one image only. That's the image of the platypus, which I have shown very quickly now. And once this is done, a forward pass is done, we already have the outputs ready. So we can get the output through the output stored, because this was defined in the function, and that is stored in the variable activation. So once we get the outputs, we can remove the hook. So that's what happening here. The shape of this is obviously 7 cross 7, and there are 2048 ones, because this is a final convolutional layer, and there is a size of 2048 channels there. And now let's display this. Okay, so this will kind of show what does the output look like. Okay, so this is original image. I have not scaled it or normalized it, that's why it looking not that great, but this is the image, and this is the output that we are going to see at the last kind of convolutional layer. I just need to check whether we have, I don't think we have run this line. It was actually picking up the ReLU, this line which was run earlier. So we will rerun this convolution in a moment, but before that, let me just quickly show you the result. If I have chosen ReLU as the output, so the very final layer, the final ReLU in the final convolutional layer, it looks like this. So there are few channels only which are relevant, all others are blanked out to 0, and these channels are looking at certain regions in the image, for example many points on this particular platypus in this case. So let me go back and change the target layer to the convolutional layer instead of the ReLU layer, and run the forward hook again. These are all same. So we'll wait for the image, and you can see the image now. So it is now the outputs of the final convolutional layer is what we are seeing here, and obviously it will have negative and positive values, and that's what we are seeing here as well. So earlier we saw the output of ReLU, which will suppress the negative values and only keep the positive values, and then it was looking like a much cleaner image in that sense. Okay, so just to reiterate, what we did is we identified a layer, we extracted the weights of that layer directly, and then displayed it. That's one way to view the weights of the kernels. The other interesting aspect is the outputs of these convolution layers or the ReLU layers or whatever layer. So for that, we need to identify a layer, then we need to attach a forward hook to that layer, we need to pass the image through the entire neural network, and then get the outputs which are hooked, and then display it as images, which is something like what we are seeing over here. Okay, so there is an interesting work by Andrich Karpathy where he has actually designed a convolutional network, a very basic network in JavaScript. It's something like this. This is the network. It's not any standard ImageNet classifier, but it's a very simple network with few convolutional layers followed by a fully connected layer with softmax with 10 classes. And this was kind of trained on the CIFAR 10 dataset. And what is he's going to show here is all the layers with the weights visualized in the below part. So let me pause the training or whatever running part here so that we can freeze on an image. So in this, it's a horse image. And what we are seeing over here, the colored one here is the gradients on the image. So how do you calculate this is we hook the gradients similar to we hook the activations, and we can do a complete backward propagation after the forward propagation. So once you do that, all the gradients are available for us to kind of take out through the hook operation. So what he has done is he's displayed the gradients as well as the activations together. So this is the input, of course, and the corresponding gradient for this particular class, whatever the predicted class, you do a back propagation all the way up to the image, and if you display that, that's what you're seeing over here. So obviously we can see there is gradients happening everywhere in the image, but possibly the more severe gradients or the high value gradients are on the horse in this case. And this is the activations or the output of the first convolutional layer, and there are 16 of them, and the size is 32 cross 32. So the no pooling, no striding here, so you can see over here, and the corresponding gradients are displayed here. And what we are seeing over here are the weights of these kernels. There are 16 of them, and the size of the kernel is 5 cross 5, and if you display them, these are the weights, 16 of them, and the corresponding gradients here. So once we have the convolutional layer, we apply ReLU on that, and you can obviously see the difference between these two. So this is only keeping the positive values, the negative values are all kind of truncated to so that the minimum is always 0. The corresponding gradients are over here. So once the ReLU is done, we typically do the pooling, and that's what we are seeing, the reduction in the size compared to this, there is a reduction in size by 2. And then again it will be followed by a series of convolutional layers, and you can see for yourself what is happening inside. And the final layer is of course a fully connected layer, and then it will be followed by a softmax layer giving you 10 predictions in this case.